All right. So good afternoon, everyone. Welcome to the Institute of Theoretical Physics located in Paris-Saclay. So in this institute, a number of research fields are studied from statistical and condensed matter physics to cosmology, particle and mathematical physics. And we are interested in trying to understand how quantum technologies, including quantum computers and quantum simulators, could potentially be useful to solve long-standing problem in some of these research fields. So with the the financial support of a European project called Quantum Internet Alliance, we took the initiative to organize a conference series to try to answer this question. So what we propose is a series of 5 conferences given by renowned researchers having both a deep understanding of ongoing efforts as well as a long-term vision along this line. So our first speaker is Professor Ignacio J.I.Cirac. Ignacio is a director at the Max Planck Institute for Quantum Optics in Garching, Germany, where he heads the theory division. He's also an honorary professor at the Technical University of Munich. Ignacio is working in several research fields, including quantum optics, quantum information, and quantum many-body physics. His work has been widely recognized and awarded, for example, by the Benjamin Franklin Medal already in physics in 2010, the Wolf Prize in Physics in 2013, or the Max Planck Medal of the German Physical Society in 2018, just to name a few. So to give you 2 examples of Ignacio's contribution, I would say that the impressive progress that we are witnessing in trapped ion quantum computing or in quantum simulation using ultra-cold atoms trapped in optical lattices, they would not have been possible without Ignacio's contribution. So for all these reasons, we are very happy to have Ignacio with us today. I would like to specify that if you want to ask questions to Ignacio, you will have the possibility to do that. And for that, you just need to use the chat. And after Ignacio's talk, I will simply read them and ask them to Ignacio. So with this, Ignacio, I would like to sincerely thank you for having accepted our invitation. And now the floor is yours.
So thank you very much. Let me share my window first, and I hope that you can see this now. So can you see my presentation?
I perfectly see it, yes. And
okay, perfect. Okay, well, first, let me thank you for this very kind introduction, and also thank all the organizers of this conference for this very kind invitation. So indeed, we are living in a very exciting moment. So for some of us who have been working for over 20 years on quantum computing, to see that now some of the dreams, at least, I mean, part of them, are becoming reality, mainly because of the experimental advances that took place during the last 10 years or so. We're very happy to see that. And it's, I think that the question that you're asking in this conference is a very important one. So how can these quantum computers, quantum simulators, or analog quantum computers can help us to solve some problems in physics or in chemistry or in science in general? And indeed, my belief is that out of all the applications that people are talking about for these first generations of quantum computers, the ones related to solving problems in science would be probably the most important ones, if not the only ones. So this is still to be seen. And so part of my talk is to convince you of that. I guess that you don't have to be convinced, but to give you maybe some extra arguments for that. And then I want to set up, like, so what do we know about that? So I want to present what are the algorithms and that we have now mainly to solve many-body problems like the ones that appear in these areas that I mentioned before. So how do they compare with classical algorithms? So where can we have, like people call exponential advantages using quantum computers? Also talk a little bit about analog versus quantum simulations, accumulation of errors. So this should give us a picture of so how in the last 3 to 5 years things will develop and would be able to address some of the problems that are important in physics. And at the end, I will just briefly mention some ways of using these systems that people are building in the labs for problems in condensed matter physics, in high energy physics, as well as in chemistry. Okay, so let me start with something that it's obvious to all of us, is that quantum many-body problems are very hard to solve with classical computers, at least if you cannot do some perturbative arguments or you're in regimes of strong interactions and so on. And this occurs in many fields in physics or chemistry, like when you have a molecule made out of many atoms, many electrons, or you have a material where there are many electrons as well, or in high energy physics where you have a quantum field theory, but as soon as you discretize it, this behaves like having a many-body quantum system that is interacting. I mean, all these problems share the property that so typically you want to solve them with a classical computer. The first thing that you do is you discretize. So in the case of chemistry, you discretize in terms of orbitals, or you could also discretize space. In terms of materials, many of them, since they have some periodic structure, they already discretize. So you just have to use the lattice corresponding to the lattice of the material. In higher energy physics, you can discretize space or use lattice gauge theories in order to have a discretization. But all of them at the end, or most of them at least, end up in having an abstract problem, which is like a lattice in which you have quantum systems in the vertices or in the edges of that lattices, and you have a description of the interactions in terms of either a Lagrangian or a Hamiltonian. And what you have to do is if you want to predict physical properties of that system, then you have to basically find what are some states, ground states or the evolution states, dynamical states of this system. So even if you make the simplest description in which these quantum systems that appear in the lattice are qubits, then you already are confronted with the main problem in many-body physics, namely that if you want to predict the properties, you will have to write a state, just this represents the state of your system, and you write it in the basis, in the spin basis, in the computational basis. Since there are 2 to the power n configurations of these qubits, then it will be described in terms of 2 to the power n complex coefficients. So describing this system requires typically to compute these coefficients, and this brings up 2 main problems. The first one is that in order to store these coefficients, you need an exponential memory in the number of qubits, and the number of qubits typically related to the volume of the system that you have. So you have an exponential growth of the memory with the volume of the system that you want to describe, and as soon as you have something like 30 or 40 qubits, then there is no memory in all the computers that we have available to store those states. The second problem is that on top of that, each of the coefficients you want to compute, you will have to perform at least one computation for each of the coefficients. So the computational time will also be exponential in n, the number of qubits. So we have a very bizarre situation with quantum many-body problems, that if we want to deal with them in a classical computer, we have a double exponential overhead, one in memory, the other one in time. In fact, as I will mention later on, so for some purposes, you may want to put some restrictions in the memory. So imagine that you say, well, I don't want to have a memory that is larger than the number of baryons in the universe. So this is a restriction. And so then you can see that you can still solve problems, but by trading time. So then the scaling with time is worse. And it's very simple to see that for typical problems, if you do that, so you lead, for example, the memory only to grow linearly with the number of qubits, then the computational time grows like 2 to the n to the power n, so something like super exponential. Of course, this problem of simulating many-body systems with classical computers was recognized by many people many years ago. So one of them was Richard Feynman, who was in a very visionary paper already gave a possible solution. So he said, well, at least the problem of memory can be solved if we would now store the state of these qubits in qubits themselves. So use a quantum system in order to describe a quantum system. Use a quantum, in his case, computer, to store and manipulate the states of a quantum system. And this is much more efficient because, as I mentioned before, the number of qubits that you will need in order to describe n qubits will grow linearly with n. And now, depending on the problem that you want to solve, then the time may scale or linearly with n or exponential or whatever. But you see already that because of the memory growing linearly with n, even if we would have an exponential time in solving with a quantum computer one quantum many-body problem, there would already be an advantage with respect to a classical problem because, as I mentioned before, if you impose some conditions on the memory, like linear, that it can grow only linearly with n, in a classical computer, it takes a super exponential time. So, in fact, I mean, this applies to both kinds of simulations. So actually, one now could distinguish two kinds of ways of simulating quantum many-body systems. One would be digital, in which you would just use a quantum computer that is based on quantum gates and acting on qubits in order to simulate whatever properties of your system. The other one would be analog, in which you would take a system that you can tame very well in the lab and then engineer the interactions between the qubits on your system in such a way that they correspond to the interactions that you want to study. So you have a problem Hamiltonian, and then take your quantum simulator, take these qubits and make them interact according to that Hamiltonian. And if you can do that, then you can simulate in a more analog way the problem. And well, in fact, I mean, we don't have digital quantum computers, but we have, I mean, noise intermediate scale quantum devices, like the one used in experiments by Google, for example, or in ion traps and some of the systems. And I mean, the questions with these devices as well with analog computers is that there are errors. And so one question is whether in these first generations of quantum computers, even though they are not scalable, still we can take this quantum many-body system, simulate, and do some computations or obtain some results which go beyond what we can do with classical computers. So I want to address some of these problems in this talk, and so that's why this talk has two parts. And the first part is about quantum algorithms for many-body quantum systems. So I will assume that I have a lattice in whatever dimension, and I would assume for simplicity that I have local interactions. So the Hamiltonian that I'm giving, it's a sum of Hamiltonians, and each of them is acting on some region of the lattice. And I will talk very briefly about algorithms for different problems. So for the dynamics, to predict the dynamics of a system, also to predict the ground state properties, also the finite energy properties and the finite temperature properties of my systems. And then at the end of the talk, so I'll talk a little bit about some specific problems and analog quantum simulators and how one could address or trying to address these problems experimentally with cold atoms in optical lattices. Okay, so let me start with the dynamics. And the problem is very easy to formulate. So you have you're giving the lattice, you're giving the Hamiltonian, you're giving some initial state which is easy to prepare. So for example, this could be just the product state of the qubits, all the qubits in the state 0. And then your goal, and you're giving some observable. And so the goal is to compute the expectation value of your observable with the state that is the one that is generated by your Hamiltonian after some time t out of the initial state. And in order to formulate this more precisely, so then you prescribe an error epsilon for the value of your observable, and then you would like to see how much the computational time grows with the number of qubits for a prescribed value of this epsilon. So again, you're giving the Hamiltonian, you're giving the initial state, you're giving some observable, you're giving some prescribed error epsilon, and now you grow and grow and grow the system and see how the computational time grows with the system size. And actually, one of the first quantum algorithms that exist was exactly to solve this problem with a quantum computer. It was given by Setzloith in '96. And so what he said is something, actually, he formulated a little bit more precisely what Feynman already formulated in his problem, in his paper. And so what he says, well, what you could do with a quantum computer is to start with this easy to prepare state, this product state, prepare your computer in this product state, then evolve it according to this Hamiltonian in terms of quantum gates, and at the end measure this observable in your quantum computer, then repeat the procedure many times, and at the end compute the average of your measurement, and this would give you a good estimation of the of this expectation value. And so the difficult part here was only to see how you can compute with a quantum computer the evolution of a state. And for that, well, he says, well, if my Hamiltonians here commute, then it's very simple, because I can write just the exponential of the Hamiltonian as the product of the exponential, and each of them is acting in a small region, so I can translate this in terms of quantum gates. So this would be a sequence of quantum gates. And if the Hamiltonians don't commute, then we can make them commute, kind of, just by using totalization. So just by dividing the time in very small times, and then just assuming that for small times, then the Hamiltonians commute, then you can write it now as a sequence of gates, as I mentioned before. Now you'll have to do many more gates. And however, I mean, you can check that the error scales like t squared divided by m, the discretization, and so everything scales correctly, so that if you fix the error to some prescribed error, then at the end the computational time in your quantum computer would scale like the number of qubits that you have square, like the time that you want to simulate square, divided by the error. Actually, there's a square here that's missing at the error square. So you already see that this is extremely efficient. So with n qubits, you can simulate the evolution of n qubits with a computational time that only scales quadratically, let's say, with the number of qubits. Now, in the meantime, people have developed more efficient algorithm, and the most efficient algorithm that I know is this one that was presented a couple of years ago, and they managed to have an computational time that scales like the number of qubits, the total time of the simulation, and the logarithm of 1 over the error. So this has a much better scaling, and this shows that indeed, I mean, for dynamics, having a quantum computer can be very efficient. Now, whereas the first algorithm can be easily used in niche devices, because it's very simple just to take this totalization and convert it into gates, the second one is much more sophisticated, and so there is an overhead that you will have to use. And I guess that only if you have a scalable quantum computer, a fault-tolerant quantum computer, this would become useful. Anyway, so in the case of dynamics, it's very clear that we get an advantage. So what about now, if you're interested in equilibrium properties of our many-body system, so for example, zero temperature. So the problem, you can formulate it in a very simple way. So you're giving the Hamiltonian again, and you're interested in, if you look at the spectrum, the lowest energy, the lowest eigenvalue of your Hamiltonian, and in the eigenstate, and the physical properties of the eigenstate corresponding to the smallest eigenvalue. So again, you're giving some observable O, you're giving some precision epsilon, and your goal is to compute this expectation value in the ground state with this precision epsilon, and then you would like to know how the computational time, the number of gates that you have to produce, scales with the number of qubits that you have in your system. And I mean, this problem actually turns out, that was shown long ago, that is what is called QMA hard. So this means that it's very likely that this computational time, even in a quantum computer, grows exponentially with the number of qubits. So QMA is a complexity class of problems that is equivalent to NP, but for quantum problems. So these are problems that in a quantum computer take an exponential time, but but if you want to check them, then you can do it efficiently with a polynomial time algorithm. In any way, so this means that this would be the scaling of ground state systems in general. Still, compare to the scaling of a classical computer, just imposing the same memory resources to the quantum computer is better. And so now here the question is, how much is this alpha? You see, if the alpha would be 100, then this would be practically impossible. If alpha would be 10 to the minus 4, then it would be very feasible. And so this is why now there are algorithms that give different values of alpha. And so I think that probably, some of the best one, or the best one in the market at the moment, has the scaling that alpha goes like 1 over 2. So that's some specific algorithm that was built for that. And it depends on the gap. So this works only if you have a gap and the gap is just the energy difference between the ground state and the first excited state. So unfortunately, these algorithms that people have figured out are difficult with NIS devices and analog, and that's why people have looked at some other algorithms which are user-friendly, and also that may not scale exponentially. And these are what are called heuristic algorithms. So these are algorithms for which you cannot prove that they will work, but maybe you use them in a problem, they will work. And for some problems, there are good reasons that to think that they will work even very well, that the computational time would not be exponential, but rather polynomially with n. So one of them is the adiabatic algorithm. And the idea here is that if you have a problem in Hamiltonian that you want to solve, then you actually figure out some other problem which is easy to solve. For example, one in which the qubits don't interact with each other and for which you can compute the ground state easily. In this case would be like all the states in zero. And now what you do is that you deform the Hamiltonian, the initial, this simple Hamiltonian to the problem Hamiltonian, and you find a deformation in such a way that the energy levels now conserve the gap, and then you now do this, you start preparing the initial state, the ground state of your simple Hamiltonian, and now you change very slowly the Hamiltonian, then according to the adiabatic theorem, then the state will follow, and then at the end you will be in the ground state of this problem Hamiltonian. So in this way you can prepare this ground state, and then you measure it, and measure these expectation values, and in this way you could have a quantum algorithm. I mean, the main drawback of this, apart from that, the fact that this heuristic, is that sometimes it's very slow. So having, I mean, the dependence with the gap is bad, and also how it grows with the number of qubits, it grows like the number of qubits to the square or something like that. So that's very slow in practice. And if you have a quantum computer that has errors, so the longer it takes, then the more errors you have, and therefore the fact that it's slow is a drawback. This is why people also came up with a variational algorithm. So these are algorithms very similar to the quantum algorithm, to the variational principle that we use in quantum physics, in which you start again with a very simple state. So like, for example, with a product state, all qubits in zero, and then you set, you apply some gates, but these gates depends on some parameters, and the goal is to find these parameters in such a way that the global state would minimize the energy. So what you have to do is to measure the energy and then do some minimization. And it turns out that, I mean, naively, this has the advantage that for some problems they are faster than the adiabatic algorithm. However, they require many measurements, and it's, I mean, humongous amount of measurements. And the second question is that nobody ensures you that by that your variational family would be a good family to describe the ground state of the system. It's the same the same thing happens with variational principle when you use it in quantum physics. So, I mean, some time ago, so we thought a hybrid algorithm that would combine the variational and adiabatic algorithm, and the main idea here is to take a adiabatic algorithm, but you see that if the gap is very big, then you could go faster. So you can change the Hamiltonian faster, and only when it gets smaller, then you should go slower. But the gap, it's something that you don't know. So you're given the Hamiltonian and you don't know what is the gap, and it's as difficult to compute as to solve the whole problem, the manybody problem. So the idea here is to do some measurements in such a way that they will tell you whether you can go fast or small. So if you want to put the speed at which you change your Hamiltonian as variational parameters, and therefore you just do a few measurements, and with that you can find, I mean, optimal ways for this adiabatic algorithm. So, I mean, maybe just look at this. So, plot here. So what we took is a Hamiltonian that is non-integrable, but that we can solve with tensor network methods. We can simulate the dynamics very well, and therefore we can simulate a quantum computer running that algorithm. And so what we saw is that the time in order to get some prescribed error with this algorithm can be sped up by a factor of 10. So just by using this variational method with few measurements. So we believe that this is a good method that could, I mean, decrease the time, and therefore the errors that you will have in this variational quantum, in these adiabatic quantum algorithms, and also reduces the number of measurements that are required. Okay, so I was talking about dynamics, zero temperature, and I want to move into finite energies, finite temperatures, and that's some work that we published recently. And so again, the problem is the same as before. So you're giving some observable, and then you would like to compute the expectation values of this observable up to some prescribed error, and you would like to see how the computational time grows with the size of your system. And now this state in which you want to compute may be some state at some given energy, or maybe some Gibbs state, so some thermal state. And so one problem would correspond more to what we call the computation in the macro-canonical ensemble, and the other one in the canonical ensemble. Of course, there are some subtleties, like, for example, we'll talk a little bit more about that, but here, if I give you some energy, that since you have a discrete spectrum, you have a finite system, then this means that these have zero probability that there is an eigenstate at this given energy. So in order to formulate this problem appropriately, then you have to give some variance, so you can have not exactly this energy, but you could be at some energies around that, and so the computational time would depend also on the variance that you're allowing here. And right, okay, so how do these problems, the computational resources, scale in a quantum computer? And it's very easy to show that they are also exponential, and in particular because they include the zero temperature. So if I specify some energy, which is the ground state energy, then I'm back to the problem that I was considering at the beginning, and this was exponential. And for a canonical ensemble, I specify as a temperature zero temperature. This would correspond to the properties of your ground state, and therefore I'm back to the other problem. So in general, this will scale exponentially. Of course, there could be some heuristic algorithms that solve in a better way, and I'll talk a little bit about that. But in principle, they scale exponentially, and some of the algorithms that people have proposed to solve these problems actually do scale exponentially in the general case. However, what we know is that, for example, in the case of energy or in the case of temperature, if the energy goes to the center of the spectrum, or if the temperature goes to infinite, then these problems can be solved very efficiently, because then, the infinite temperature for a set of qubits is that all of them are completely depolarized. They are in the identity operator in the mixed state, so that's trivial. So one could expect that there is like a phase transition in complexity, that as you increase the temperature, then for some temperature, then for a quantum computer, then they become easy, or as a function of the energy, as you increase the energy, there is some energy for which the problems are not exponentially hard, but are polynomially hard. The same would be expected for a classical algorithm in a classical computer. However, as I will argue, is that for a quantum computer, this will occur much earlier. So there will be some, let's say, ranges of energy, a big range of energy, where one would expect that for a quantum computer, this would be easy, and for a classical computer, it would be difficult. So I want to talk a little bit about that. And so let me now concentrate on the finite energy, the microcanonical, and specify the problem a little bit more precisely. So we are giving now since I want to scale my problem as a function of n, then I will not give you the value of E. What I have to give you is the energy density, the E divided by n. So this is what I fix. I fix some energy density. I fix some observable. So this could be some local observables, magnetization, sigma c, or whatever. And what I would like to do is to compute this expectation value with a state which has an expectation value of the energy equal to the extensive value, so n times the energy density. So you give me E, small e, then you give me n qubits, then the energy will be n times E. So I would like to have a state that has this expectation value, and it has a variance, which is delta. And with a prescription, this epsilon, prescription precision. So here the question is, how does the computational time scales with n? And also with epsilon and delta. And then, so one question that one can ask, oh shit, I'm sorry, I'm in a talk. Okay, so then the one question that you can ask is, so what is a reasonable value of delta? And so should delta be like a square root of n or 1 divided by n? And so it turns out that people have shown that for some physically relevant problems, so in order to get the the convergence to the thermodynamic value of the microcanonical ensemble, then you should scale delta as 1/n. And so I'll come back to that. So now one can also ask, what about classical algorithms? So how do classical algorithms perform with this problem? And some time ago, together with David Hughes and Marie-Carmen Bagnul, so we studied that in terms of tensor networks. So we look at how would a tensor network algorithm scale in order to solve this specific problem. And so what we found is that just making arguments with entanglement and things like that, that the computational time would scale with a minimum of the exponential of 1/delta or exponential of n. And so you see that in order to obtain the relevant information, if delta has to scale like 1/n, these classical algorithms scale exponentially with n. So these are classical algorithms require an exponential time in general for this problem. Now, so in some other paper, we came up with this with a quantum algorithm that could address this problem. So let me just sketch what is the main idea. So the idea is, first, you're giving this E that you compute as n times the intensive energy. And let's imagine that there exists a state that is easy to prepare that has this value of the energy. For example, a product state. Of course, if the energy is very low, you will not be able to do that. But if the energy is sufficiently high, then there would be a product state or an easy to prepare state that will have this energy. And of course, this gives already a restriction that you cannot solve for every energy, but we know that it has to be like that, because for the ground state energy, we know that this is a QMA hard problem. Okay, now this product state, or this easy to prepare state, of course, will have a variance which would be too large. So typically a product state has a variance which scales like a square root of n. So this will not be 1/n or something like that. It would be much, much bigger. So the second part of the quantum algorithms is to apply a spectral filter. So in the same way that if you have a broadband light, then you can filter, and then you will have a very, very narrow band light, then you can do something similar with a quantum computer with that, and I'll show you how to do that until the width, so the variance of the state is delta. And then it turns out that to prepare state is very difficult for a quantum computer, still polynomial time, but for these first devices, it will, require creation of Schrödinger cats and things like that. So this is why the third part of the algorithm is to never create the state. Yes, to use the quantum computer, a quantum simulator, in order to get the pieces that you need in order to compute these expectation values. So you don't need to prepare the state in order to compute the expectation value, but I will show in a second. Then you can use like the quantum computer as a subroutine to compute some pieces that would allow you to compute this expectation value. So let me go through these 3 points and one after each other. So the first, I mentioned, take a state that is easy to prepare, right? And so, for instance, we could take a product state, and if there exists a product state with this energy, this is very easy to prepare. So you just prepare the first qubit in one state, the second qubit in some other state, and so on. And then you have to make sure that the expectation value of the energy is that one. So, of course, this is not possible in general because the product states cannot go all the way to the ground state energy, because the ground state is not a product state typically in the systems. So this would make a restriction. And so this will tell you that the energies that you can study with this method have to be larger than some minimal energy. And now maybe one could say, well, but if we want to use energies that are lower that corresponds to product state, what we could do is to use the algorithm that I mentioned before to prepare the ground states, right, heuristically, and then this would be a good starting point. Yes, indeed, this is possible. However, this is not provable. So if I give you some energy, then it would not be possible to tell me beforehand whether you can reach this energy with this method. So actually, there is another this is a restriction, but there is another method that can be used. And so maybe let me mention first is that if you have product states, so people have figured out what is the lowest energy that in general you can get with a product state. And so they have figured out that in general, this is the ground state energy divided by 9. So that's very far away from the ground state. So this means that this method would have very much, a lot of restrictions for the range of energies. It could also work on energies that are here close to the center of the spectrum. However, I mean, first of all, this is general, so these are not short-range interactions. So for short-range interactions, you can take the proof and modify a little bit, and then you get that this is 0 divided by 3. So this still, I mean, not very good. But what it's better, so what you can do now is to say, well, let me not take a product state of the qubits, but let me block the qubits. So let me take, for example, blocks of 3 by 3 qubits, 3 by 3, 3 by 3, 3 by 3, 3 by 3. And for each 3 by 3, now let me find what is the lowest energy of the Hamiltonian acting on these 3 qubits and prepare that state. So this state, of course, it's easy to prepare. It only has few qubits. And you can also compute what is the ground state because it has only 3 qubits. So you can do it efficiently with a classical computer. And now you can say, so what happens if I start growing these blocks? And then you can show that if you log 1 over dn, where d is now the dimensions, the space dimension of your system, then still the number of qubits that you will have in the block would be of the order of n, because it would be log 1 over d to the power d, because you're in d dimensions. Then they're of the order of, log n. And so the dimension of your Hilbert space would be 2 to the log n, so it would be n. So you could still compute what is the best, the lowest energy in each of the blocks. You could also prepare it efficiently because each of the blocks has only log n qubits, and so I mean you would take an exponential time in log n, so it's polynomial in n, and you can easily show also that the energy of that state can approach E0. I mean, like 1 divided by log 1 over d over n. So this means that this method would scale and will approach this E0 as much as you want. So altogether, this means that this method can be used in order to prepare these microcanonical states at very low, for a very wide range of energies, and puts already some ranges of energies for which you have an efficient algorithm that you can use in order to compute physical properties. Now, still, I mean, this was the first step. Still, I mean, the energy variance will be too big. So the second part is how to reduce the variance, and the idea here is to apply a filtering operator, so something that takes the initial state that you prepare and that it filters the energy. So this could be, for example, a Gaussian filter, something which is centered around this energy and has a width delta. And you can see that if you apply this operator to the state, then the width of the final operator will be really of the order of delta. And however, this operator, this filter, is not unitary. So this means that it cannot be encoded in a quantum computation. So the trick here is to expand it in terms of a kind of a discrete Fourier transform, a finite one, because the width is finite. And now you write it in terms of a Fourier transform, then you see that what appears here is just the evolution operator. So you see that now what you have to do basically is to prepare a state which is a linear superposition of times of the initial state evolved for different times, and each of them has a weight. So you would be able to create these linear superpositions in which you have like this initial state, the initial state evolved for some time, the initial state evolved for twice the time, initial state 3 times the time, and so on. You would have that state, then you will have the state which has this variance. However, producing this linear superposition is hard and requires algorithms that are very complicated. And this is why we have the third method that does not produce the state, or the third part of the algorithm, that use what is called time series. So, I mean, this is not so important. And so the idea is now to say, well, at the end, what we want to do is to compute some expectation value with that state. So we would like to compute this quantity. So what we can do is just replace this formula in this expectation value, and then you can find that this expectation value can be written in terms of quantities like that. Quantities in which you start with the initial state and you evolve for some time, and then you look at what is the overlap with the initial state, or in which you have some initial state evolve for some time, and then you walk backwards on the other side, and then you compute some expectation value. So if you would be able to measure these quantities A and B for different times the n, then you could replace this in this formula because everything depends on this quantity. So that's the idea, is to measure with a quantum computer these quantities A of t and B of t, and never prepare the state. That's what I told you before, that you don't have to prepare the state, but rather just to compute some quantities with a quantum computer. And so, I mean, how do you compute quantities like that? Well, this is, I mean, the absolute value is what is called log-Schmidt echo. So you start with initial state, evolve, and see what is the overlap with the initial state you started. So you have some initial qubit configuration, then you evolve, and then you see whether you have the same or not. You measure. If you have the same, you assign a 1. If you don't have the same, you assign a 0. Repeat many times, average, and this will give you the absolute value. And about the phase, I mean, there are some quantum algorithms that do that, and in some cases it can even be computed classically for if you have certain symmetries in your Hamiltonian. Okay, in any case, so this problem of finite energies, as I mentioned before, then actually you put together what I told you before, then you have a provable algorithm that has a computational time that grows polynomially with n with 1 over delta and 1 over epsilon. And so you see that if you want to compute thermodynamic properties in which delta goes like 1 over n, is still polynomial in time, so it's better than the classical algorithm, and so you have a speed up also for finite energies. Now, what about finite temperatures? I'll be very briefly that. So you can use similar ideas here. And so you can formulate it now that you're giving a temperature, you're giving an observable, you're giving a precision, and then they want to compute the expectation value up to this precision and see how this scales with n. And so for that, we have an heuristic algorithm, and this heuristic algorithm, what it does is that it uses the standard Monte Carlo method problem that is used in classical computers. Quantum Monte Carlo is called. However, this quantum Monte Carlo has a problem with some specific Hamiltonians. This is called the sign problem, and so what the algorithm that we propose actually overcomes the sign problem. So it uses a quantum computer to get rid of the sign problem in quantum Monte Carlo. So let me tell you what is the idea very briefly. So at the end, you want to compute this expectation value of the observables, and then you can rephrase this expectation value also in terms of some things that are positive and some other expectation values. And now what you do here is a sum with respect to product states. So the idea is if you take the trace, you can take any basis to take the trace, you take the product states, and in the product state basis, then you see that you have a sum over product states, and then you have some expectation value. You have also some energies here that's maybe not so important, but the point is that this, you see that there is a sampling problem. So you are able to sample according to this probability, these are positive quantities, then you will be able to compute this quantity, this quotient. And so that's the idea, that at the end, all the quantities that appear in this formula, again, can be written in terms of this A and B. So what you would use is to take a product state, a random product state, and now with this product state, then you would compute some probabilities. And like, for example, you flip one of the product states, one of spins of one of the product states, compute the new probability. And depending on that, you accept or not accept the move, classically with a classical computer. And if you accept the move, then you compute this quantity also with this A and B that you have measured. So the idea is that you just run a standard quantum Monte Carlo algorithm, but in order to compute the probabilities and the expectation values, these are the places where you find the sign problem, then you use a quantum computer which overcomes the sign problem. There is no sign problem in that, so you can show. However, I mean, there is more measurements, so at the end you have to make more measurements because you have to sample. And let me insist that this is a heuristic algorithm, and the reason is because it's using Monte Carlo. Monte Carlo is also heuristic. So in Monte Carlo, it may happen that you have a distribution that is difficult, even a classical Monte Carlo, that is difficult to sample from. And so here you could still have the same property, but still, I mean, as I mentioned before, I mean, what it does is like the normal Monte Carlo, but avoiding the sign problem. Okay, so let me finish in the last 7 minutes talking a little bit about analog quantum simulation. And so in the difference I mentioned between digital and analog quantum simulation, so the digital is with a quantum computer with quantum gates that are digitalized. In an analog is that you would take a system and then you would engineer the interactions in such a way that they correspond to the problem that you want to solve. It's like in analog computers and digital computers, so the analog quantum computer or the analog quantum simulation is like an analog version of a digital computer. So what are advantages and disadvantages? So analog. So the analog is typically not universal. So typically in some experiment, you can engineer some interaction, but not all possible interactions. So you will be able to simulate some kind of problems. there is no error correction there. So I mean, you have some error, you'll have to, by hardware and maybe some error mitigation, you'll try to decrease it as much as possible, but you will not be able to scale it up, to scale the quantum computer up. However, the dynamics is most efficient. And the reason is that when I mentioned before the problem of dynamics, of quantum algorithms for dynamics, I mentioned that the idea was for a digital quantum computer was to digitalize, so to trotterize the evolution of the Hamiltonian, to make small time steps. But this has a very big overhead in the number of gates in a digital quantum computer. So you have a Hamiltonian, then you will have to discretize, and for each infinitesimal time, small time, then you have to apply gates. So at the end, you apply many more gates. And of course, if the gates have some errors like they have in these NIS devices, then they will accumulate. And that's why this quantum simulation is not so, let's say, so useful in NIS devices at the moment because of this discretization problem. However, in analog quantum computers, I mean, you just tune the Hamiltonian, prepare the initial state, and you don't have to do anything actively. You let it evolve, and it will evolve according to that. They're easier to build, these analog systems. And for some quantum computations, they are more natural for fermions. So you have, for example, fermionic atoms, or you have electrons in your quantum simulators, then you have fermionic systems. So for example, you want to describe now quantum chromodynamics, including matter, with a quantum computer or with an analog quantum simulator, then if you don't have fermions, then you will have to pay the price and big overhead, because you will have to simulate with bosons these fermions. Now, let me just briefly mention that what about the errors? And I think that, I mean, the fact that I mentioned before that there is no error correction shouldn't be such a big problem. And the reason is because, I mean, even though errors are extensive, so you have a Hamiltonian that you want to simulate, and then you have an error, then the error will be per lattice size. So at each lattice size, let's see, there will be an error. Like, let's say the Hamiltonian that you want to apply has some error, and since you have n terms in your Hamiltonian, you will have n terms in the errors. So the total norm of the error will scale like n. So even if epsilon is small, then if you multiply by n, will be extensive. So this means that for a very short time, then you will not evolve according to the original Hamiltonian, and this will not be longer a perturbation. However, in quantum simulation, at least for some problems, you're interested in observables that are intensive. You're interested in the energy per particle. You're interested in the magnetization per particle, because you're interested in large systems, in thermodynamic limits. And it turns out that this somehow makes also the fact that the error is extensive not a problem. So that these magnetizations, in many cases, scales like epsilon, not an epsilon times n. And I mean, there is not a proof for this statement. That's something that you can see in certain cases. And one very clear case is this experiment that took place in 2002, in which in the group of Ivano Bloch and colleagues, they were simulating the Bose-Hubbard model, some particular model. And if you look at the experiments, so the Hamiltonian they were simulating had huge errors. So this epsilon was of the order of 20%. So 20% times n, and they had something like 100,000 atoms. But still, you see, whatever they are doing here, they wanted to see that there was a quantum phase transition, that if they change the parameters at some point, something changes abruptly, and this is what they observed. These are real pictures of what they observed in some densities. And you see that nevertheless, I mean, you can observe the phase transition, even though the errors were big. And so that's, I mean, one of the hopes for this quantum many-body system simulation, that even if you have analog simulators, even if the errors are extensive, then at the end, I mean, you will be able to observe the physics because you're interested in intensive quantities. Now, a few words about different problems. Now with cold atoms in optical lattices. So this is an analog quantum simulator in which atoms are held by some optical lattices, and they can tunnel in this optical lattice from one place to another one. And if you write, starting basically from first principles and projecting the real Hamiltonian into the low energy sector, then you get a Hubbard Hamiltonian. And so this means that with this system, it's very natural to simulate Hubbard models as they appear in condensed matter physics, and then you can change boson, fermion, spin geometry dimensions, etc., etc. So what about high energy physics? Well, in high energy physics, of course, it's much more complicated. You have matter and gauge fields. The theory is relativistic. It's also gauge invariant. And also, I mean, for this quantum simulation, one would like to have a Hamilton formulation, but it turns out that this is not a problem. So the first thing is that the fact that you have matter and gauge fields, it means that your simulation should have to combine bosonic and fermionic atoms, or the degrees of freedom. The fact that this relativistic is not a problem. You don't have to move these atoms at the speed of light, but rather use a lattice, because we know that in a lattice, then, for example, you have a lattice with a dispersion relation like is like a sine. Then if you go to the part where the sine has a constant slope, then there, I mean, you get kind of a continuous limit that is relativistic. So people have figured out how to do that. The gauge invariant is not a problem because these atoms have conservation laws, like in collisions, conservation of angular momentum, and then you can encode the gauge symmetries, abelian and non-abelian, in some of these conservation laws that appears in the case of atoms. And well, for Hamiltonian simulation, I mean, that's very long ago, Kogut and Saskin had the lattice gauge theories formulation of that, and that's why you could simulate using cold atoms lattice gauge theories. So maybe in 1+1 dimension, this would be relatively straightforward. And so you just have to use bosonic atoms and fermionic atoms. So the fermionic atoms, I mean, just represent your particles and antiparticles, and positrons use QED, for example. It would be electrons and positrons, and with the you can have in the links the bosonic atoms, and then with the bosonic atoms you can basically describe the gauge fields. And what is challenging is to go to higher dimensions. And the reason for analog quantum simulation is that in higher dimensions, all these lattice gauge theories have plaquette terms corresponding to the magnetic field in QED or QCD. And this would require four-body interactions, whereas the natural interactions with these simulators are two-body interactions. So this means that in order to get out of two-body interactions, four-body interactions, then you have to use perturbation theory and go to something like fourth-order perturbation theory. And so therefore this will become more difficult, and that's why I think that even though they are difficult, I mean, this will happen at some stage, but they are much more difficult. And finally, just a few words about quantum chemistry. So what about analog simulation of quantum chemistry? Well, at the end, what you want to solve is a problem that it's like this one here. You have some electrons that are interacting with the nuclei, and imagine that the nuclei have an infinite mass in Born-Oppenheimer approximation. So this means that there are some like external potentials, and these electrons are attracted to these external potentials, and at the same time they have to repel each other. So it's very easy with atoms in optical lattice to put some external potentials that have 1/r loss. This is done with holographic lenses. And so this would simulate now the attraction of the electrons, which would be now atoms that are fermions. However, the difficult part here is so how to make neutral atoms to interact according to a Coulomb interaction, a potential that decreases like 1 divided by the distance. And so for that, what you could do is to, emulate electrodynamics and quantum electrodynamics in which photons mediate the interaction between fermions. So in the case of cold atoms, then you can put some bosons in the lattice in such a way that they mediate the interactions between the fermions. And if you do it in the right way, then actually you can get that an effective theory that this decays like 1/r. Well, in any case, so let's say that for quantum simulation, I mean, there are many motivations, but I would highlight the one of benchmarking theory. So at the moment, so people like us who are developing also classical methods for simulation based on tensor networks and other theories, then one of the drawbacks that we have is that we don't have some benchmark experiments to benchmark our theory. And I think that quantum simulators, if they are built, or the ones that are being built, would be very useful for that. So to finish up, so I was talking about the quantum simulation is arguably the most suitable application of quantum computers. I was highlighting that already with analog and these NICS devices, I mean, some quantum simulations in condensed matter physics and high energy physics probably are likely to happen relatively soon. And I was highlighting the advantage of analog versus NISQ for some of these problems. I also mentioned that there's still probably they're also very useful not only to solve problems, but also to benchmark theories that would allow to solve these problems, but still many challenges to be addressed. And so here's a picture of my department and the persons that were involved in what I was talking here, Marie-Carmen Manuel, Benjamin Giffer, and Cyril Liu, and we have some external and long-standing collaborations with many people abroad. So thank you for your attention.
Thank you very much, Ignacio. Yes. So, the problem with online talks is that we can't hear people, making noise out of at the end of a talk. But at least I can tell you that people here who are physically here were very happy about your talk. So thank you very much for that.
Thank you.
Now, if you have time for a few questions, I can eventually have a look list of questions we got by email, on the chat, sorry. So the first question by Alex Grillo is the following one regarding analog computers not being universal. Does it depend on the underlying Hamiltonian? As far as I remember, we do have some families that would allow universal computation, no?
Okay, so first is that depends on the platform that you have. So for example, you can have a platform, let's say experimental, which you can only have global operations, so that you have translational invariant or homogeneous interactions. And in that case, then you could only simulate problems that have translational invariance. And so this will not be general. Even though, it turns out that even if you have only access to translational invariant systems, then you can simulate, you can have a universal quantum computation with that. But there might be some restrictions, some more restrictions. So for example, you can only put magnetic fields in the Z direction, or you can also measure in some directions. So there will be some restrictions. That's the first that will not make it universal. And the second thing is that because of the lack of error correction, then even if it would be universal, it would be completely useless. So you want to factorize numbers with analog quantum simulator, then for sure you will need some error correction. And then since this is very difficult to implement there because of the reasons that I mentioned, then I think that would be more difficult.
Yeah, maybe as a follow-up question, Ignacio, can you, you already mentioned it, but why do you say that, is there a principle that prevents us to have an error correction on an analog quantum computer?
Yes, so I will give you a standard answer, even though there may be ways around it. So the idea of our quantum error correction is that, you see, you have a continuous system. In a quantum computer, you apply a gate, which is 45 degrees or 47 degrees rotations or something like that. So it's very continuous. And the error correction, what it does is discretizes the gates, because you just measure sigma x, sigma y, or sigma c errors, and then you do something in a discrete way. So error correction is kind of very discrete. You measure in some basis, and depending on that, you apply a gate to that qubit. If you have analog quantum simulator, then you could say, well, you could also make measurements and after some time step in each of the qubits and do something. But basically you will be building a digital quantum computer with that. So then this of course goes back to the digital quantum computers, because now there might be some not, let's say, universal error correcting, not fault tolerant error correction schemes that can work for quantum simulations. So people have been talking about mitigation of errors and spin echoes or photon echoes. There are some techniques that can be applied. However, I'm not sure that there is a scaling theorem. In the case of fault tolerant error correction, there is a mathematical theorem that tells you that under some conditions that you can have universal quantum computation for a big system, as big as you want. And for analog simulations, I don't think that they exist unless you at the end discretize everything and then you're back to the digital quantum computer.
Thank you. So there is another question appearing on the chat, correct? Question, there's no filter, so I simply read it. This is a question from someone called Colin. The most successful search algorithm classically is Google PageRank. Will a computer be better in running the Google PageRank algorithm?
Okay, so let me maybe, I'm not answering exactly that question, but I think that's a good point. So the problem that was mentioned here is a classical problem. It's a classical optimization problem. It's not a quantum many-body problem. So this means for these kind of problems, then we don't have this double exponential gain that we have to start with, like in any optimization problem. On top of that, in many optimization problems, the algorithms that we know are Grover-like. So there is a polynomial scale, like a advantage with respect. And so this means that if you have errors or you have anything else, then probably you will lose the advantage. So that's why I'm quite skeptical about the usage of these kind of first generations of noisy generations of quantum computers to solve optimization problems and to have speed up. This is why in quantum many-body system there is a chance, because of this double exponential. It's not only exponential in time as compared to optimization, but it's also this exponential in memory, and that's why there is a big difference for these systems. Now, the question now could be, what happens in the long run? If we build a scalable quantum computer, then the first thing is we will forget about quantum simulators in the same, or analog quantum computers, in the same way that when we had digital classical computers, we forgot about analog classical computers. So these analog quantum computers and simulators, I mean, will run for a time until we have scalable quantum computing. But whenever we have a scalable quantum computer, so can we use it for problems like this rank page of Google? And so my question is that I still hesitate. And let me tell you why. Is that if there is an exponential speed up, maybe yes, but that's very unlikely. It's more likely that there is a polynomial speed up, like a kind of Grover algorithm helps. But the Grover algorithms, I mean, has a polynomial scaling, so it means that it doesn't have such a big gain. Whereas a fault-tolerant quantum computer has a lot of overhead because of fault-tolerant error correction. So now you want to compare these two, the classical algorithm with the quantum fault-tolerant quantum computer, you have to take into account the overhead that you have. Because the speed up is not so big, then you will see that this crossing point at which the quantum computer beats the classical computer may happen already when you have, let's say 10 to the 30 bits. And these are, I mean, we'll never have this number of bits, so this will never be useful. So that's why, I mean, for this kind of problem, one have to be a bit careful and really do a comparison that is fair.
Thank you again. Any other question in the room, in the chat? Last chance for everyone before I ask a final, very general question to you, Ignacio. Mm-hmm. So I'd like to ask you, Ignacio, once I give you a universal quantum computer, what would be your physics problem that you'd like to solve with it?
Okay. So I mean, I would like to. I think that where we find really applications would be in chemistry. So that's my belief. I think that in high energy physics are already very good methods. There are still problems that have chemical potentials, evolution, which will be very useful. But where they can, and there will be some problems for that, and also in condensed matter physics, there are in Hubbard models, but already with tensor networks can get very good results for Hubbard models. So I would say that probably problems in chemistry where, I mean, at the moment, it's really a random kind of the algorithms, how they work. So there would be most of the applications would be there.
All right, thank you very much. So with this, I think I would like to sincerely thank you for your talk and for being with us, Ignacio, during this first conference. It was a real pleasure to have you there. And yeah, thank you very much.
Okay, thank you very much. My pleasure. Bye-bye.